equations.
Yeah. Hello everyone. So this is going to be a nice little exercise in a 30-minute demo about equations. So equations is a package for code that allows you to write functions that use dependent pattern matching and recursion. And I'm going to just gradually walk you through the features of the language and what the equations provide you. So besides definitions, you will also get reasoning principles on the definitions that you write. So the most trivial example I could find is defining negation on the inductive type of Booleans. If the Boolean is true, you return false. If it's false, you return true. Yes? Bigger? Slightly bigger? I can do this. Better? So as you can see, in equations you don't write pattern matching definitions, you write equations. So clauses that tells you how do you map a left-hand side to a right-hand side. But in the end, once the equation's definition has been type-checked, it is compiled down or elaborated to a pure cop term. So if I look at the definition of neg that is generated, you will see that. Can you see at the back, the bottom of the slide? I cannot really go higher. So the negation is just defined as a regular cop term, as extracting over Booleans and doing an if then else. Nothing special is happening there. But you get more out of an equation's definition. You also get reasoning principles. So if I want to do a proof on my negation function, so here I'm going to show that negation is involutive. So if I apply it twice, I get the identity. So I could go the usual way and just do pattern matching on my case analysis on my Boolean. Then I will get two goals, one for true, one for false. What equations give you for each definition is rewrite rules that correspond to the clauses. So you can use rewriting instead of regular computation if you want to simplify your goals. So that can give you more control than what just pure computation calling a reduction tactic like CBV or CBN gives you. So I can do that. Actually, all of the clauses are put in a database whose name is the name of the function. So I can call this simp tactic, which is basically auto-rewrite with all the equations associated to a definition to solve this goal. Okay. And that will just apply as a reduction rules for the function everywhere. And I can finish my proof this way. Okay. You also get another reasoning principle, which is the elimination principle for the function, which is actually built from a graph representation of the function. So if I print the graph associated to negation, where you can easily guess what it looks like, it is an inductive relation between the arguments of negation to the result type, which is Boolean in this case. And it's a very simple function here, so you just get a truth table basically for negation. That's two constructors, the graph, one which maps true to false and one which maps false to true. And from this graph and the fact that the function respects it, which is automatically proven by equations, you get an elimination principle. And basically when you use the elimination principle, you can get a kind of synthetic reasoning principle on your definition that will redo in your proof the pattern matching or recursion that was done by the function and leave you with just the leaves of the program to prove, assuming your recursive calls have the right property by induction. Okay, so our negation is pretty simple. When we are applying this functional elimination principle to a call here of the negation of B, we refine at the same time the argument B to either true or false and the result to false or true. Okay, so I can just apply this eliminator using this funneling tactic, which looks up the eliminator for the function and applies it. And in that case, indeed, I'm refining both arguments and results at the same time. I'm not applying any reduction here. It's really a synthetic reasoning principle that gives you that. So it can be very useful for complex functions to have this synthetic reasoning principles. You also get shorter proofs, smaller proof terms for them. Okay. So let's build up a little bit and move to a list. So I'm defining my own notations for list here. I will show you how you can define recursive functions with equations. So there is support for associating notations to recursive definitions and actually writing down your equations using these notations. So you can do that by reserving first a notation for here I'm defining my own variant of list concatenation. I'm declaring some notation for it, and I'm binding in the definition of the program the notation to the actual global name that is associated to this variant of concatenation. And then I can write my patterns using the notations on the left-hand sides and on the right-hand sides. Okay, and as you can see, you get, you can define usual structurally recursive definitions with equations. You don't need to annotate or use a different keyword for non-recursive or recursive definitions. If the equation finds out that you're using syntactically the name of the function recursively, then it assumes that you want to do a structurally recursive definition. Okay, nice. You also get, of course, the same reasoning principles out of it. So the equations, but also an eliminator. So here the eliminator becomes a bit more interesting. So I'm going to show you an example what it gives you. So here I'm proving associativity of this concatenation, and I'm just going to eliminate this x plus plus y call, and I'm going to get two cases. So the first one is trivial. For the second one, it's a recursive call in the definition of x plus plus y, and you get the right instantiated induction hypothesis for that recursive call that you can use to finish your proof. So it really helps also with when you have this functional elimination, you can just apply it at the beginning of a proof and solve the rest by standard rewriting and automation. So it really simplifies inductive proofs about recursive functions. Okay. One thing that often happens when you are doing elimination is that you're doing elimination not on a purely on a goal that's purely built out of variables. You might have instantiated arguments to your function. So functional elimination also supports that. So it will, when you do functional elimination on an instantiated call, so something like L plus plus nil, plus 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 nil, you need to remember information about the arguments of the call in each of the sub-goals, so that your goal remains provable, and functional elimination does that for you. Okay, so in that case, my induction hypothesis actually tells me that the second argument, when I do the recursive call of that function, my second argument is still the nil list, and I can use that to prove my property. Yes?
Can you go slowly and remove the O2?
Yes. So here you're refining this L plus plus nil call. First case, L is going to be replaced by nil in both sides. And the other case, the recursive call is made with the second argument being specifically nil. Okay. Let's now move to the left. So we write these functions by pattern matching, but of course when you are doing programming, you might scrutinize other results during your computation. So we have a way to add another pattern to the set of patterns you want to scrutinize. So this is done using this with construct, which basically does a nested pattern matching. So it adds a clause that you can look at. So here I'm defining filter on this, quite usual function. In the const case, I need to check whether the predicate holds for the head of the list or not. And depending on that, either keep the element or remove it. So you can do that using this with construct. So in general, you're doing dependent pattern matching, so you might be refining patterns that came before when you pattern matching on this last argument. It's not the case here for brilliance. You can also abbreviate these patterns by putting a vertical bar to say the patterns did not change from the enclosing filter ALP here.
What's the reason why you need to put bound P?
What?
Why do you need to put P in the words?
P here?
P is in the words. Why do you need to put it there?
I'm looking at P of A.
Oh, right. Okay, it's applied to the. Okay. Yes.
Yeah, it's like this, right?
Yeah. Yes.
So again, the elimination principle is synthesizing this additional pattern matching that you're doing. So what you get from the eliminator is actually three possible cases. The first case for the empty list, and then the two cases where you additionally know that the head of the list has a property. Okay, so I can prove a property like this, like filtering a list by the constantly true predicate gives me in fact the original list. And I will get three cases which correspond to the three leaves of the program. The first case is trivial. In the second case, you actually know, you keep the information around that you did a test on P of A to know if it's true or false. And in the first case, it's going to be true. In the second case, it's going to be false. And you're going to need that information, that equality, to prove your theorem in general. And it is provided just by the eliminator. So you don't need to. That's something you would do when writing a proof on a program, using the remember tactic, for example, to remember that you did a test. It does that for you. Okay. So another thing you can do is define auxiliary functions inside your recursive definitions. So typically, when you're working with accumulators, you will want to write first a function on an accumulating function and then call it with a specific initial argument. So you can do that in a single definition in equations, and also get an eliminator that provides the right reasoning principles of this. So here I'm showing the example of list reversal, which is first defined using an accumulator. So I have this auxiliary go function, which just accumulates the reversal of the list until the initial list is empty and I return the accumulator. Okay, so it's just a standard auxiliary function, like a lead-bound auxiliary definition. But when you want to prove things about it, you can use this eliminator to do the proof about both the accumulating function and the top-level one at the same time, by basically providing the kind of loop invariant to the function. So here I'm showing that this accumulating function implementation is the same, is essentially the same as a traditional, the specification of list reversal. And I can do that in one go using this eliminator. So basically, I need to give two predicates to my eliminator. One that talks about the top-level function, so that's basically the end result of the whole proof, and one that talks about the accumulating function inside, which is here the loop invariant that actually the result of the whole accumulating function is the reversal of the rest of the list plus the current accumulator. Okay. And again, that also simplifies the way you can prove functions about this accumulator. So it really forces you to think about the invariant that you want of this function before trying to go through and prove your results. Okay. One last example on this auxiliary definition is that you can also write well-founded definitions with equations and even well-founded sub-functions. So this is an example taken from Haskell's library, where we are doing a prime test by returning the right result for 0, 1, 2, and then starting from 2, we are doing a proof search to test if some number is a prime. And this works by well-founded recursion. You could not write such a function, which is actually increasing as a recursive code, using just structural recursion. So this provides you ways to import functional programs that use implicitly well-founded recursion inside it's just accepted by equations. So here I'm using a specific mode of equations, which is equations question mark, which instead of using obligations, gives you directly goals in the proof refinement code that you can. So here you have one obligation to show that this recursive call to the worker is correct. You can do that just in the proof mode. Okay, and that actually just relies on linear arithmetic.
Does this thing need to be defined, so I don't feel ID?
Probably because I want to compute with it later. I'm not sure if it will get stuck or not. No, it's not getting stuck. Yeah, and even if these functions are defined using well-founded recursion, you can still compute with them inside code. So here I'm applying this prime to a list of natural numbers and getting a result. Okay, am I doing on time?
Yeah, 5 more minutes, 5, 6 minutes.
5?
5, 6.
Okay. So fast. So you can write also dependent pattern matchings in equations. So here I'm showing you an example of deciding the equality of natural numbers. So it's a standard program. We are pattern matching on both numbers at the same time. And what's interesting here is that when we are looking at the result of the recursive call in the successor case, we can pattern match on the equality proof that is given back to us in the case the sub-numbers are equal. And this is an example where the patterns on the left, I mean the previous patterns are getting refined. So here by pattern matching on this equireference, we know that N and M must be equal, so they are unified. And so the M becomes forcibly the N argument, which is the only well-typed instantiation of that pattern. Okay, this works just as well as any other equation definition. Let's move to more complex inductive families. So you can write pattern matchings on index values. So here, traditional example of vectors. You get the same kind of dependent pattern matching notion that you have in ACTA, where you can reason about the fact that some parts of your inductive value are inhabited or not, depending on the indices. So this is just a regular map function on vectors. But more interestingly, you can write what would be partial functions, usually, like the state function, which takes a vector of size n plus 1 and returns a vector of size n. The notion of pattern matching allows you to write just a single clause, and it will tell you that there is only a single clause to consider in that case because the vector is non-empty. And this version of equations is actually relying on a no confusion property on an inductive type that is necessary to simplify this dependent pattern matching. You're really relying on the fact that some constructors are different to have these high-level definitions. And basically, it says that an index inductive type, like vectors or fin, the equality in the Kant's case is just the equality of the head of the object and the tail of the object, but not of the indices, which are kind of forced arguments of the constructors for vector. So using this improved notion of no confusion, you can actually combine dependent pattern matching without adding any axioms, which we are plaguing definitions by equations in previous versions. So for example, you can define some diagonal function on square matrices, so made out of vectors of size n or vectors of size n. This requires to do pattern matching on a vector data type. So in the first case, I'm taking square matrix of size 0, so I'm actually the diagonal of this is going to be the empty list. But in the case that the square matrix is of size n plus 1, so we have n plus 1 columns of rows that are of size n plus 1 as well, so we can directly pattern match on the first line or column to get the top left side of the matrix, and use that to compute the diagonal. And this is accepted by equations. So it's really relying on this notion of no confusion of constructors to type check these clauses. And again, you get the same equation out of it and reasoning principle on the definitions. Okay, I don't think I can tell you much more about diag. What I wanted to show is that, what?
3 minutes.
3?
Yeah.
Okay. So equations provide you also with tactics that reflect in the tactic world what the equation can do when you type check different pattern matching definitions. So you get this depending tactic that applies the dependent elimination inside the proof mode. So I can show that fin of 0 is empty, for example, using dependent elimination. There are no constructors in the type fin for the index 0. More interestingly, for vectors, I can define by tactic if I want the decidable equality on vectors, assuming I know how to compare their elements. So I would go about this in a standard way by doing induction on the first vector. But then I have two cases to consider. The second vector has to be of the same length. So to solve that case, I have to show that vectors of size 0 have to be v-nil. Okay, has to be the empty one, so I can independently eliminate that. And in the second case, I have a second vector of size n plus 1. And here you would like to say, oh, disrupt it and name the head of that or that vector as A prime and the tail as V prime. There actually, before this, there was no tactics that could really give that power. If you use inversion, you would have to give cases for both for cons and nil.
Yes, and directly use notation for cons.
What?
If you would have a notation for cons, would you also directly use it there?
Yeah, you could. Yeah, you could use that.
Ah, cool.
So here you get really the same notion of pattern matching inside the tactic mode, where you just give the patterns that correspond to the type of the thing you're eliminating. And of course, you can name things correctly. Okay, so this notion of no confusion that is part of equations now allows you to solve no confusion problems that were not solvable before without axioms. So traditionally, if you start to do proofs about vectors, you will come to a point where you need to simplify an equality like this, like you have the same, two vectors which have the same head but that different subvectors are equal, and you want to know that then it means that P and G prime are equal. If you try to do this with standard tactics like inversion, you get an equality between existentials that you cannot simplify without using an axiom like K. Whereas the no confusion principle that is part of equations already gives you exactly the notion of no confusion you would expect, that you just have that the heads are equal and the subvectors are equal, and you can continue simplifying with that without using any axioms. So if I look at the assumptions of this EQ-deck function, lemma, it's closed under the global context. I did not use any axiom to simplify this. I'm going to stop here on the demo. Just to summarize, so you get high-level function definitions by dependent pattern matching and recursion. It supports the square clauses, also pattern matching lambda, so you can write anonymous pattern matching functions in the bodies of equations. You have this improved no confusion principle, which basically it is derivable only for forced arguments. So you can check if pattern matching on an inductive data type, which is index, is going to need K or not by trying to derive this no confusion principle. Basically, it says that all forced arguments they don't need to be equal. We don't need a proof of equality on them. We also support mutual and well-founded recursive definitions. It's all compiled down to axiom-free terms, so you can reuse them in your developments and not be scared about importing axioms. It's also there is a version that is also compatible with interpreting equality in type. If people do homotopy type theory, for example, they want that. And we have this functional elimination principle that synthesizes the behavior of the function, the recursion behavior, and the pattern matching behavior. And we have this Saylor dependent elimination tactic. So it's all available on GitHub. You can install it from OpenM. There's a gallery of programs that show more advanced example of the use of equations. And just, if I have time, on perspective, so there are many extensions that we would like to do on equations. One obvious one is adding co-pattern matching. So right now it's only pattern matching on inductive data types. We would like co-pattern matching for defining co-fixed points. Something that is really missing is a refinement, an interactive refinement mode, like Agda has or Lean has inside IDEs, to be able to write these dependent type programs in an incremental way, which is really necessary. We have steps toward using the size chain termination principle to show that equation definitions are well-founded. Maybe we will go to a cleaner white space sensitive syntax, because right now it's a bit hard to parse. So I got lots of reports from users that don't like the syntax because it's full of delimiters. And I would like to introduce, to integrate this notion of no confusion and dependent elimination inside the traditional interpreters of SS right now. In the end, the idea of replacing the function tool which provides similar functions. Okay.
Thanks. Questions?
How good are the error messages?
They are getting better with each release. They can still be improved, I guess.
Can you write down the motives in the pattern matchings, or you don't actually need to specify motives here?
So you never need to specify the motives. They are always in front. Yeah, you don't need any annotation.
Okay.
Yeah. And that's because we force each, maybe I should show it in one which has one function. Yeah, we force each definition to come, each sub-definition on which we want to do pattern matching to come with its completely specified prototype. And from that we can always infer the motifs of the eliminations.
I was wondering about the simplification behavior of these equations. So, as I understood correctly, you have the simp tactic for doing simplification instead of doing normal simplification. Yeah. Could you say how that compares, like, in practical use or also performance-wise, with, like, when you have a function which is defined in the normal way and which uses the normal simplification?
Well, you're using logical reasoning instead of computation, so it's going to be slower, for sure. And the proof terms are going to get bigger. But you can also use simplification with them. There are regular calc functions, you can also reduce them. You might see, if you try to unfold manually, you might see some auxiliary definitions that are used to justify dependent pattern matching. But all of this reduces away. So you have the same conversion that you would get naturally get from a calc definition, the same thing.
Okay, but are they by default like simple never, or when you do simple would they?
So there are switches. By default, you can make them all opaque. Here, in that example, I use this set equations transparent, which tells after the definition of equations, make them transparent so they can be reduced. So it can be a bit problematic if you use simple carelessly. You might see unfolding that you don't want to see.
Okay.
So you have control over that.
Okay, thanks.
Last question.
Do you have coverage, or do you plan to have coverage for nested recursive functions? When you have a recursive call over the result of a previous call?
Yeah, it does work. Yeah.
It does work.
Right, let's thank Matthieu again.